Chemical equilibrium. Equilibrium is a state in which there are no observable changes as time goes by. Chemical equilibrium is achieved when the rates of forward reaction and reverse reactions are equal and the concentration of the reactants and products remains constant. There are physical equilibriums and there are chemical equilibriums. Consider the equilibrium between N2O4 dinitrogen tetroxide and NO2 nitrogen dioxide. We can start the reaction with nitrogen dioxide. Notice as the concentration of NO2 decreases, the concentration of N2O4 increases until equilibrium is reached. The reaction can be started the other way with N2O4. In this case, N2O4 decreases and NO2 concentration will increase, again until equilibrium is reached. In the third case, we start the reaction with amounts of N2O4 and NO2. Once again, equilibrium will be attained with time. This table shows various experiments where the concentrations of NO2 in moles per liter or molarity and N2O4 again in molarity were started with NO2 or N2O4 or with both. Equilibrium concentrations were calculated and the ratio of concentrations at equilibrium is shown in the last column. Notice that they remain constant. The equilibrium constant K sub C, the equilibrium constant based on concentrations for this hypothetical reaction is as follows. K sub C is equal to the concentration of C in moles per liter raised to the C power. The C power is the coefficient of substance C, times the concentration of D to the D power and divided by the reactants, concentration of A to the A power, concentration of B to the B power. It's always defined as the concentration of the products over the concentration of the reactants. Here we have the equilibrium between ammonia plus oxygen yielding nitrogen and water, all in the gas phase. The expression is the concentration of nitrogen squared, the concentration of water to the sixth power, corresponding to the coefficients of nitrogen and water, divided by ammonia to the fourth power and oxygen to the third power. Again, consider this hypothetical reaction and the equilibrium constant. Let's see how K varies and what that tells us about the reaction. If K is a number much greater than 1, the equilibrium will lie to the right and favor the products. It's called a product-favored reaction. If K is much smaller than 1, the equilibrium will lie to the left, and now we have a reactant-favored reaction. Let's see how Kc relates to a forward reaction and a reverse reaction. For N2O4 dissociating into NO2, Kc is NO2 concentration squared divided by N2O4. If we reverse the reaction to NO2 in equilibrium with N2O4, then we write Kc prime, concentration of N2O4 divided by the concentration of NO2 squared. How does Kc and Kc prime relate? They are reciprocals. Kc equals 1 over Kc prime. Kp is an equilibrium constant based on partial pressures rather than concentration. Here we have 2 moles of SO2 reacting with O2 to form 2 moles of SO3. We write an expression K sub P, equilibrium based on partial pressures, equal to the partial pressure of sulfur trioxide squared divided by the partial pressure of sulfur dioxide squared times the partial pressure of oxygen. Kp can be related to Kc. Kp equals Kc times RT that's the gas constant and the absolute temperature, raised to the delta N power. Delta N is the number of gaseous products minus the number of gaseous reactants. In this case, it's 2 minus 3, so delta N is equal to minus 1. Heterogeneous equilibria involves materials in more than one phase. In this expression, we omit the concentration of liquids and solids. Here we have the reaction of P4 with 6 moles of Cl2 to yield 4 PCl3. Notice that the P4 is a solid and the PCl3 is a liquid. The expression simplifies to 1 over the concentration of chlorine to the 6th power. Chemical kinetics in equilibrium. For any reaction, the forward rate is equal to K sub F, the specific rate constant, times the concentration of A times the concentration of B squared. In this reaction, the reverse rate is equal to K sub R times the concentration of AB2. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Therefore, we can write the following expression. We can make a ratio between the forward rate constant and the reverse rate constant. That will equal Kc, and Kc of course is equal to the concentration of AB2 divided by the concentration of A times the concentration of B squared.